Hi, welcome to the LoRa workshop on Educational Engineering Academy. This is Ahmed Tariq, and in this workshop we will introduce you to an interesting wireless communication technology called LoRa. We will talk about it theoretically, and at the end of this workshop we will build a simple project that shows the LoRa capabilities. So let's get started. With the Internet of Things booming and billions of devices connecting worldwide, things are getting trickier for the folks who design and keep up with wireless technologies. There are many wireless technologies besides just Wi-Fi like Bluetooth, Zigbee, and Z-Wave, and cellular networks like 4G and 5G. And each one plays a part in making all these IoT devices connect with each other and work properly. These different technologies are good at different things. Some can handle big chunks of data, which is great for streaming videos and music. Others are better for keeping an eye on things or making things work automatically. The kind of wireless tech used in wearables like fitness trackers often needs to save battery life, while different technologies might be better for hospitals, cars, farms, or even just tracking stuff you don't want to lose. Even though all these wireless technologies are useful and give our IoT devices cool features, they all have weak spots. The main issue usually comes down to a choice: how far can I send information, or the range, compared to how much information it can send at once, or the data rate. For example, this graph shows us a regular Bluetooth headset might reach up 50 meters, but it can only send a few bits of information, or the bandwidth of it is very low. This is fine for listening to music, but not enough for streaming a video. Wi-Fi and cellular networks can send a lot more information at once because they have a higher bandwidth. This lets them handle video streaming and lots of internet traffic. But there are catches. Wi-Fi uses more battery power, and cellular might not reach as far depending on the exact tech. So the many wireless technologies out there give us all sorts of options for building cool IoT devices. But to make sure everything works its best, we need to understand the trade-offs between how far it can send information and how much it can send at once. This way, developers and engineers can pick the right wireless tech for each unique IoT project. The link budget refers to the overall expense incurred in establishing connection between 2 points, often used to compare different wireless technologies. In simpler terms, it measures the total cost of transmitting a signal from point A to point B, and it's measured in dBm. In practice, determining link budgets involves complex formulas and calculations, taking many factors into consideration beyond just bandwidth and range. Factors such as geographical location, environmental conditions, and obstacles such as buildings can cause signal loss by obstructing or reflecting radio frequency signals. Additionally, amplifier gain, antenna gain, and impedance mismatch between cables and antennas can influence signal strength and receiver sensitivity. So, numerous variables contribute to the overall link budget calculations. This diagram, we observe that LoRa in the bottom right has an exceptional low link budget, especially considering its impressive range capabilities. This makes LoRa an excellent choice for communicating with IoT devices that operate on extremely low power, where preserving battery life is crucial. Achieving this is largely due to minimizing data payloads, which is typical for sensor type endpoint devices. Alright, so LoRa is an application of chirp modulation. While this modulation is not new, the minds behind LoRa took this exciting technology and transformed it into a powerful solution for the challenge of the Internet of Things. You may be familiar with how radios work, using techniques like amplitude modulation or AM and frequency modulation or FM to transmit sound. AM and FM are dealing with analog signals like sound, music, etc. Chirp modulation, on the other side, is a more sophisticated technique. It falls under the category of digital modulation, more specifically a subcategory called spread spectrum modulation. Unlike AM and FM, which deal with analog signals like sound waves, digital modulation deals with digital data, zeros and ones. This data is encoded by manipulating some aspect of a carrier wave like frequency or amplitude according to a set of rules. The spread spectrum modulation is a technique that takes the concept of digital modulation a step further. It deliberately spreads the data signal over a much wider frequency band than the information itself requires. Something like a message written in tiny letters spread out across a giant billboard. That's kind of like spread spectrum. There are several benefits to this modulation. First is the reduced interference. In crowded environments with lots of wireless signals, spread spectrum makes it harder for other signals to interfere with your data. It's like hiding your message amongst a bunch of background noise. Second, the improved range spreading the signal allows for lower transmission power, which can improve the range, especially in situations where high power might not be desirable. Increased security, because the spread spectrum signal appears like noise to an unintended receiver. It offers a layer of security by making it difficult to detect or intercept the actual data. So, chirp modulation is a specific type of spread spectrum modulation where the carrier signal frequency continuously changes over time, like a rising or falling whistle. This chirping pattern adds another layer of complexity and helps LoRa be suitable for long range and low power communication in the world of IoT. The name chirp modulation is not just a coincidence. LoRa's technology draws inspiration from the chirps of birds. Think about it. How easily can you distinguish the chirp of a specific bird species, even in a chorus of different bird songs? Their chirps travel well and cut through background noise, make them recognizable. This is not unique to birds. Bats and dolphins use ultrasonic chirps. Sounds too high for humans to hear. For similar reasons, extended range and easy distinction from surrounding noise. The remarkable properties of chirps translate into the world of radio waves. LoRa's chirp modulation excels at decoding signals even when buried in noise. This superpower is a key factor behind LoRa effectiveness. Technically, a chirp is a signal where the frequency constantly changes, either rising or falling over time. But what does that mean compared to the more familiar modulation techniques in radios like AM or FM? This graph shows an amplitude modulation wave and a frequency modulation wave. Both waves use a carrier signal, typically a high frequency sine wave, to transmit information. The key difference lies in how they change and modulate this carrier signal to encode the information they carry. There is a horizontal axis representing time and a vertical axis representing the strength or the amplitude of the signal. In an AM modulation, the information is embedded in changing the height or the amplitude of the carrier wave. The wave itself resembles a series of peaks and valleys, with the height of each peak or valley corresponding to the information being sent. Think of it like raising or lowering the volume of a sound wave to represent the original sound. On the other hand, FM modulation keeps the overall shape or the sine wave of the carrier signal constant. The height is constant. The information is encoded by changing the frequency, how often the wave oscillates per unit time. This is the frequency. So, changing the frequency of the carrier wave. As you can see here, the wave gets slightly squished or stretched horizontally. These variations in frequency, not the height of the wave again, represent the information being transmitted. Traditional radio uses AM and FM to transmit analog signals like music and sound. These techniques work by varying the radio wave itself to represent the sound wave. Chirp modulation, however, is a completely different, where information is encoded as a series of zeros and ones. In LoRa's case, chirp modulation takes these digital bits and transforms them into unique chirps. Each chirp represents a specific combination of ones and zeros, or symbols. We will see that later. These chirps are then sent one after another on top of the carrier wave. This combination of digital data, encoded as chirps and a carrier wave, forms the heart of LoRa's communication method. Explaining how chirps work in LoRa can be tricky, as it's not easy to explain it in detail in this limited time workshop. But I will do my best to describe the LoRa technology itself simply. The LoRa frame. While a signal chirp forms the basic building block of LoRa communication, a valid LoRa message, technically known as a frame, needs a more intricate composition. This parallels the construction of a musical piece where various instruments contribute to the overall melody. A LoRa frame combines different chirp sequences, each serving a specific function. In this drawing, each blue line stands for one chirp. As time goes on, these chirps move through different frequencies. Now, in a LoRa message, there are three groups of chirps: preamble, sync word, and data. Each group does something different and they use different kind of chirps. The preamble and sync word, this is the preamble and this is the sync word, use a simple kind of chirping to get the attention of the receiver. They are like a doorbell to say, hey, pay attention to me. These parts do not carry a lot of information. They are just there to be easy to understand, to be noticeable and easy to understand, even if there is a lot of background noise. But the real information is hidden in the data type, is in the data part. This is where the message is hidden. The way the chirps change over time in the data part tells the radio what each symbol in the message mean. But what is that symbol? Well, in simple terms, the symbol is a small piece of information. For example, in a message saying hello, each letter of this word, H-E-L-L-O, each letter is a symbol. And digitally, each symbol is represented in zeros and ones. So each block in the data part represents a symbol. The way that chirps change helps the receiver figure out which symbol is which letter. When you start working with LoRa, you will notice that there are a lot of factors to adjust, like bandwidth, spreading factor, and coding rate. These settings determine how the signal is sent. Let's start by explaining what is the bandwidth. Bandwidth measures how fast a signal changes. It tells us the maximum amount of information that can be sent in a certain time. Think of it like a highway. A wider highway allows more cars to pass through at once. Bandwidth is measured in hertz. In theory, LoRa can use any bandwidth. However, in practical scenarios, constraints arise from the available spectrum, regulatory frameworks, and the physical limitation of transceiver hardware. Consequently, the commonly adopted bandwidth in sub-gigahertz LoRa applications stands at 125 kHz. There are chips that are capable of modulation at 250 and 500 kHz, as well as lower frequencies. In the 2.4 GHz, LoRa chips can accommodate up to 1.6 MHz of bandwidth. To choose the right bandwidth, here is a simple rule. If we use a higher bandwidth, we can send data faster because more information can pass through at the same time. If we use a lower bandwidth, we send data slower because less information can pass through at the same time. But to get the right speed of our data, we also need to think about two other factors: spreading factor and the coding rate. The spreading factor is a crucial parameter in LoRa technology that determines how the data is spread out over the available bandwidth. Essentially, it controls the rate at which data is transmitted and received, affecting both the range and the robustness of the communication. In simple terms, spreading factor is like stretching out your signal over a wider area. A higher spreading factor means the signal is spread out more, covering a wider range of frequencies. This allows the signal to travel longer distances and penetrate obstacles better. It makes it ideal for applications that require long-range communication such as rural IoT deployments or environmental monitoring in remote areas. However, using a higher spreading factor also means that the data is transmitted more slowly. It's like speaking slowly and clearly so someone can understand you from far away. But this will increase the power consumption as you spread the data and you speak slowly, so you take a lot of time to transmit your whole message. On the other side, a lower spreading factor concentrates the signal into a narrow range of frequencies, resulting in a faster data transmission. This is useful for applications that require higher data rates over shorter distances, such as smart city infrastructure or tracking in urban environments. As you can see in this chart, you can see the spreading factor from 7, the lowest one, to SF12, the highest spreading factor, and you will note that the chirp in the SF7 takes too little time, but in the SF12 it's spread over a wide range of time. Choosing the right spreading factor depends on the specific requirements of the application. Factors such as desired range, data rate, and power consumption need to be considered when selecting the spreading factor. So in summary, the higher the spreading factor, the lower the data rate. The higher the spreading factor, the longer the range. The higher the spreading factor, the slower the transmission. The lower the spreading factor, the higher the data rate. The lower the spreading factor, the shorter the range. The lower the spreading factor, the faster the transmission. Coding rate. Coding rate in LoRa technology is another crucial factor that influences how efficiently data is transmitted and how robust it is to errors. Imagine you're sending a coded message to a friend. We can either write the message in full detail, high information content, but risk errors during transmission, or you can add redundant codes for error correction at the expense of some message space, mean lower information content or lower important information content. Coding rate in LoRa works on a similar principle. LoRa uses a specific set of coding rates, typically denoted as X over Y, where X and Y are integers. For example, a coding rate of 4 over 5 indicates that for every 5 bits transmitted and received at the receiver part, 4 bits represent the actual data. There are the information bits, and the remaining 1 bit is used for error. Higher coding rate, like 4 over 5, there are some pros and cons for each coding rate. For the higher coding rate, more information per transmission, so it's faster. More data bits are packed into each symbol, allowing for faster data transmission compared to lower coding rates. Less overhead. A smaller proportion of the signal is dedicated to error correction, potentially lowering power consumption in some scenarios. The cons of the higher coding rate include the lower error correction. Fewer redundant bits are available to detect the correct errors during transmission, This can be problematic in noisy environments where the signal might be corrupted. For the lower coding rate, like 4/8, the pros of it are the stronger error correction. There are more redundant bits included for error detection and correction, which make the data transmission more robust in solutions with potential interference or noise. The cons of it are less information per transmission. Fewer data bits are included in each symbol, leading to slower data rates. More overhead. A larger portion of the signal is dedicated to error correction, which might increase the power consumption. So you need more time to transmit your full message. The optimal coding rate for LoRa application depends on the specific needs. If reliable data transmission is crucial and errors cannot be tolerated, even at the cost of slower speeds, a lower coding rate with a stronger error connection is preferred at this case. Conversely, if the speed is a priority and the environment is relatively clean with minimal interference, a higher coding rate can maximize data throughput. Coding rate works in conjunction with the spreading factor. A good rule of thumb is to combine a lower coding rate with a higher spreading factor for situations demanding maximum range error correction, even if it means slower data transmission.